Okay, I'm going to walk you through some review questions, particularly even numbers where the answers are not in the back of your text. That will walk through and focus on some Chapter 1 items in this first video, and I'll do the same for the following chapters. So to begin, question number 42 in section 1.1, find x in the triangle pictured. So we see a right triangle and we remember the Pythagorean theorem right from the beginning of the semester. A squared plus b squared equals c squared. C is of course across from the right angle, it's the hypotenuse. Then A and B could be any of the other legs, so the A and B are interchangeable. So substituting x minus 1 squared plus x squared equals 5 squared. Now every time I substitute into a formula, I always use parentheses, and this is a great habit to form if you haven't already, because sometimes this will protect you from making certain mistakes. For example, if the 5 was negative, the negative inside the parentheses is very different than the negative outside the parentheses. So that's one mistake that is saved. Another one, right here, we're squaring all of x minus 1, not just x or just 1. So when we're squaring that, that means the parenthesis unit or the quantity times itself. So x minus 1 times x minus 1 in this case, which would be x squared minus 2x plus 1. And then plus x squared equals 25. At that point, we want to combine like terms on the left side. I'm also going to subtract the 25 from both sides and have x squared minus, 2x squared minus 2x minus 24 equals 0. Since this has an x squared term and an x to the first term, we need all of the terms on one side of the equal sign, set the whole thing equal to 0 in solving this quadratic. Now, every number is even, so we could factor out a 2, or I'm just going to go ahead and divide both sides of the equation by 2, which is going to get rid of or cut each of those numbers in half, bringing us to x squared minus x minus 12 equals 0. I like factoring as the way to solve if possible. Of course, you could graph or use the quadratic formula. You can even complete the square. But factoring for me is the best. X times x is x squared. I need the factors of negative 12 that will add to negative 1. And that would be negative 4 and positive 3. Those numbers multiply to negative 12 but add to negative 1. Now, we set each factor equal to 0 and then solve each equation separately. So over here we'll add 4 to both sides and x equals 4. Over here we'll subtract 3 from both sides of the equal sign and x equals negative 3. The temptation here is to stop, but whenever we get an answer, we should check. And how we're going to check this problem is substitute the x values into the triangle. 4 minus 1 is 3, and this side being 4. So this is a 3, 4, 5 right triangle. It's a Pythagorean triple. That happens to be nice. Now if we substitute the negative 3 in, negative 3 minus 1 is negative 4. Or just up here, negative 3. We cannot have a negative distance in a triangle that exists here. So this solution, although correct for the algebraic equation that is found from the Pythagorean theorem with this case, the only value that works in this solution or in this real problem dealing with the dimensions of this triangle would be the positive value of 4. I should have mentioned this at the beginning of the video. If you have not done the problems first, I strongly suggest that you try the question, pause the video, try the question, and then check with the video to see, are you on the right track. At any point in time, you can pause, try the work, and then push play and see how this is going. This is a great way to use this tool. Next question, we're looking at this cube, and they say that the dimension for all sides of the cube is 5 centimeters. And they want the length of GD. So along the bottom here, I'm going to look at this triangle, and better would be to use the highlight tool. This is the triangle that I'm working with. Okay. And I'm going to redraw that triangle right up here. And this is a 90-degree triangle. This side is G, this is C, and this is D. I know these sides are all 5. Now, because it's a cube, I know that each face of the cube is a square, meaning every angle is 90 degrees. So this is now a 45, 45, 90 special right triangle. And the ratios or the relationships with the 45, 45, 90 right triangle is that the two legs both equal x, and the hypotenuse then is x times the square root of 2. So in this case, 5 square roots of 2 would be the length of that side. Now, of course, centimeters is our units, so the diagonal GD equals, that distance is 5 square roots of 2 centimeters. That's the exact length for the diagonal GD. Now in part B, they're asking for a different triangle, and this one's kind of cool. Let me erase the highlight there and go to a different highlight and try and show you the triangle we're looking for here. This time they want GB. So this is the diagonal that they're looking for, connecting the top corner closest to you to the bottom corner furthest away. And so I'm going to come across here, and then I'm going to connect up to B from C. So this triangle is kind of on its side, but into the cube, which is going to change up some things for us. So I will draw this triangle. Oh, I don't want yellow. This triangle I will draw in the same structure, but I'll label appropriately. This is G, this is now B, and this is C. I know that GC is still 5 units as it was in the triangle above, in the problem above. It is an edge of the cube. CB, however, is a diagonal on one of the faces. Well, we just solved for that up in the first part of the problem. So CB is 5 square roots of 2 centimeters. And now I need to find GB. Well, in this case, it's not necessarily a 45, 45, 90 right triangle because we're not looking at a square face. And both legs are not equivalent. So that's another indicator that this is not that special right triangle, which means we have to go back to the Pythagorean theorem. And so 5 squared plus 5 square roots of 2 squared equals the length of GB squared. Well, 5 squared is 25 there, and also here. The square root of 2 squared is 2, so 25 times 2, or 50, plus 25 equals GB squared. 25 plus 50 is 75. And we're going to take the square root of both sides. So that 75, or that's the same as 25 times 3, and the square root of 25 is 5. The square root of 3 is not a perfect square, so it will remain in the radical, equals the length of GB. Oh, and that is centimeters, because that's the dimensions that we were given. So 5 square roots of 3 centimeters would be the length of the diagonal GB, cutting right through the center of the cube. On to section 2 now. Page 23, there's a couple problems for you there in chapter 1. We're going to look at number 40 right now. Find y so that the distance between the two given points with a missing y value in one of them equals 5. So we need the distance formula. The distance formula again, distance equals the square root of x2 minus x1, or the difference of the x's squared, plus the difference of the y's, y2 minus y1 squared. And this is derived from the Pythagorean theorem as we went over in class. Now, substituting what we know, I like to have positive numbers. I also want the variable to be first. So we're going to call this one 0.2 and this one 0.1 if we're going to use the formula in that way. So the distance is given as 5. That equals the square root of, first the x's, 7 minus 3 squared plus y minus 3 squared. And this is to sort of show you I want that y term first and I want it to be positive. It's not a requirement, it just makes things a little easier for you. Now, 7 minus 3 is 4 squared. And this is going to be y minus 3 times y minus 3. In this first step, I do want to get rid of the square root, so I'm going to square both sides of the equation just to get rid of the radical right from the beginning and make things easier to work with. So I have now 25 equals this information. 25 is going to be 16 plus, when we multiply this these two binomials, we get y squared minus 6y plus 9. We add the 16 in and we'll get 25. So y squared minus 6y plus 25 as we combine like terms there, and that equals 25. Again, I have a squared term and a linear term, a y to the first, so we need to subtract 25 from both sides to get the this side to equal 0. And when you do, you'll notice the positive 25 minus 25 will become 0. So y squared minus 6y is what's left over. Factoring this is a little different, maybe even easier than the problem we did just a moment ago, because it just has a greatest common factor of y that will factor out or divide each term by and be left with y minus 6. Each of those will get set equal to 0 as before, and so y equals 0, and we add 6 to both sides of the equal sign here, y equals 6. Both of those are acceptable answers in this problem because we don't have a triangle that we're looking at, for example, where I need a positive side or anything like that. This is just a coordinate of a particular point that could be in a positive position or a negative position or anywhere. But from the fixed point of 3, 3, a distance of 5 units away along the, or paired up with a point having the x value of 7, y has to be either 0 or 6. Continuing on to the next section. We're going to look at 52 and 54 sort of together, as in both of these questions we're looking to find which quadrant or quadrants the terminal side of theta must be in order, first, that sine theta is positive and cosine is negative. Well, I'm going to think about the coordinate grid. Here's your x and your y, and I know that the x values are positive here, the y values are positive, the x values are negative, the y values are negative. So both are negative in quadrant 3, only x is negative in quadrant 2, both are positive in quadrant 1, but in quadrant 4 only the x is positive. So with that information, we think about sine, and we remember that sine is the y value over the hypotenuse. Cosine is the x value over the hypotenuse of which is made up of the angle, the terminal side of that angle. So we're going to just, for this sake, look at sine being y, cosine being x. So another way of asking this question is, where is sine positive and cosine negative? So the y values are positive here in quadrants 1 and 2, but the cosine values are negative in quadrant 2 only, and therefore the terminal angle would be, or terminal side of the angle would be in quadrant 2. And again, we use Roman numerals for quadrants. Down in 54, cosine again is x, and cotangent is going to be cosine, or x, over sine, which is y. And I want to know where they have the same sign. Okay. I'll start first in quadrant 1. The x value, or the cosine value, is going to be positive here in quadrant 1 or 4. But dividing the x and the y, or the cosine divided by the sine, I need their SIGN to be the same. A positive divided by a positive is a positive answer, or a negative divided by negative is a positive answer. Where if we had a positive and a negative and we were dividing, then the answer would be negative. So if cosine is positive in these two quadrants, 1 and 4, where then is cotangent positive, or the place that has the same sign? And that would be right here in quadrant 1. So quadrant 1, both are positive. Cosine being negative, the x value being negative, I don't know why that just drew there, sorry about that. Cosine being negative would be in quadrant 2 or 3. Cotangent being negative has to be in quadrant 2, where the signs are opposite. Quadrant 2. Now both are negative there. Moving on to the next section, looking here at question 34 in the problem set starting on page 39. We're going to use equivalent forms of the first Pythagorean identity in these couple questions that we're going to look at now. So we want to find cosine theta in quadrant 3 of an angle that terminates in quadrant 3. In quadrant 3, cosine is negative. That's going to be important in a minute. Now, they give us sine, and we know with that Pythagorean identity that cosine theta is going to equal plus or minus the square root of 1 minus sine squared theta. And we said that cosine was negative in quadrant 3, so in our problem, cosine theta is going to be negative the square root of 1 minus, and they gave us that sine was 1/3, but that is going to be squared. When we square 1/3, that's going to be 1/9. So I want to rewrite 1 as 9/9. That way we have the same denominator and can simplify easily. 9 minus 1 is 8. So 8/9, the square root of 8/9. The square root of 8 simplifies to 2 square roots of 2, and the square root of 9 is 3. We remember it is negative, and so cosine theta in this problem is negative 2 square roots of 2 over 3, using the Pythagorean identities. In number 36, we're going to follow a similar process. Again, we're trying to find cosine, but this time in quadrant 4, where cosine is positive. So this time, cosine theta equals positive square root 1 minus sine squared theta, or negative 4/5 squared. The negative that is being squared in these parentheses becomes positive, and 4 squared is 16, 5 squared is 25. I'm going to rewrite the 1 as 25 over 25. 25 minus 16 is 9. I can take the square root of 9 and get 3. I can take the square root of 25 and get 5. Again, our answer is positive, so cosine theta in this problem would be 3/5. Moving on to the next section. Here we're beginning to lay the foundation for verifying trig identities. One of the strategies that we talked about to do that this course so far was to rewrite as sines and cosines. So I take a look here, cotangent theta. Well, cotangent is cosine divided by sine. Not equals, minus cosecant theta is 1 over sine theta. They ask us to simplify after we've rewritten if possible. Well, here, since the denominators are the same, we can do the subtraction and say cosine theta minus 1 all over the same denominator, sine theta, and this would be a completed problem. In number 28, the directions are the same, and so we rewrite cosine theta. Tangent is sine theta divided by cosine theta, and these we're being multiplied, the cosine by the tangent, and we're adding sine theta. Cosine divided by cosine is 1, so this simplifies to just sine theta plus sine theta, which does simplify further. Since they are like terms, I can add them to be 2 sine theta. Closing out our review of chapter 1 for the midterm. Simplify this expression when we substitute 8 secant theta in for x squared. So 8 secant theta is being squared. Subtract 64 and take the square root of the whole thing. First, I'm going to square 8 secant theta and get 64 secant squared theta. And that is going to be minus 64. Now, because of this minus sign, I can't just start taking square roots of things. I must first factor out a 64 from the binomial that's here. 64 times secant squared theta minus 1, still under the radical. Now, secant squared theta minus 1 with the Pythagorean identities was the same thing as tangent squared. And that is still times 64. And we can take the square root now. Since there is no plus or minus sign and we are left with a product, we can take the square root of everything. And the square root of 64 is 8. The square root of tangent squared is tangent. Now, because you cannot take the square root of a negative, we have to consider the fact that tangent must be a positive answer. So the absolute value would be required here, and therefore 8 times the absolute value of tangent theta would be the simplest form of problem number 62. Hopefully this video has been helpful to you in reviewing Chapter 1 problems and getting ready for the midterm.